everyone, welcome to section 20. Time flies when you're having fun. At least I think we're in section 20 now. But so we're going to be talking about inverse functions today. So it's kind of odd starting with notation, but I just thought it might be a little bit easier to start with that. So we typically write the inverse of a function f as f inverse, okay? So an inverse function, so notice that I'm saying inverse functions. All right, so an inverse function, so notice that I'm saying function. So it's not just like an inverse for just any kind of map. We're just going to be talking about inverse of functions. So not only is it an inverse of a function, but then it also itself is a function. I know that sounds kind of confusing, but let me write it out. Okay. So now that I've written it all out, hopefully this makes a little bit more sense. So we're inverting a function, and then what we get out of it is also a function. Those are the things that we care about here, okay? And you might be noticing maybe that this is not always possible. So you can't just grab any function and just always assume that it has an inverse function, okay? So, and these are the only inverses that we're going to care about in this class is inverse functions. So let's start talking about what has to happen for f inverse to be a function itself. Okay. So this is going to be a nice review of our definition of function. Okay. So f inverse must send every y in our domain, remember, because we flip-flop who's the domain and who's the codomain. So that's kind of what this inverting thing is talking about, right? So you reverse that. Reverse. Okay. Must send every y in its domain to a unique x. Every element in its domain has one bow and one arrow, okay? And it only shoots that one arrow, okay? But everyone has a bow and arrow, okay? Everyone gets a chance to shoot their shot, okay? So now let's start thinking. So that's what it means for f inverse to be a function. So what must be true about f to allow this f inverse to exist? So let's start psychoanalyzing this. Okay. First off, let's think about f inverse has to send every single element in its domain y somewhere. Okay. So if I move my little face, if we look over here at maybe this part, so what happens if f doesn't hit everyone? So let's say f is not surjective. Okay, so not every single y gets hit by an element in f, in x by f. Okay, so let's draw a picture. So maybe blue will be f's actions or something. I'm not sure. Let's make it really simple and just do 3 elements in each. Okay, so let's say we have that happen or something. Okay, so now our f inverse has to send every single y value somewhere. So we'll do f inverse is green. So it has to send this somewhere, right? Every element has to get some sort of bow and arrow. And it has to go somewhere. But where is it going to go? So let's say it goes to this element. See, what's the harm in that? What's the harm in that? Well, when we do this thing that I highlighted in blue up here, so f inverse of that element is going, let's give them names. How about that? So A, B, C, alpha, beta, gamma. Okay. So we have f of f inverse of gamma. So, all right, f inverse of gamma, that's just going to be C. So f of C. All right, and then f of C, that goes to beta. Beta is not equal to gamma. Okay, so now f inverse isn't our inverse function that we wanted. Okay, so that's what happens when f is not surjective. So you can even do this with like an infinite example if they're both are. It doesn't matter. So what ends up happening is f inverse doesn't know who to send each of its elements back to. Okay, because that's what should happen here, is all these blue arrows that we draw, we should just be able to go back along them. So maybe you're an element in Y and you caught an arrow. You should be able to just throw back the arrow along the string that it came, and that's your shot that you take. Okay, and then that's how f inverse is defined. Okay, so that makes everything super easy, right? And then all these two definitions that we have here that I already highlighted, the one that I already highlighted in blue, and then the one that I highlight that I'm now boxing in with pink, then those two will be satisfied. Okay, so that's what we want to happen. So now this thing here, this has shown f needs to be surjective. Okay? All right, so what else? So let's say, let's add another element over here to our example, maybe call it D. Okay? And we'll let f hit gamma. Okay. Now we're looking better, right? But let's remember back to our definition of function. So for our f inverse to be a function, every element in its domain only gets one arrow. Okay, so it only gets to go to one place. You can't have f inverse of alpha equals a and b or something. It just has to be one. It can only go to one element, or else it's not well defined. Okay, so that's going to cause us some problems here, isn't it? If we just try to do this trick of just reversing our blue arrow, if f not injective. So now our pink thing is going to lead us to, if we try, so remember f inverse of f of x has to equal x. So if we do f inverse of f of, let's say, b. Okay, so f of b, well, that's going to get us to beta. So now we have f inverse of beta. Okay, but Danica, remember you said we could just define our functions how we wanted them to be. Okay, so let's just define f inverse of beta to be b. Let's just do that. Okay, so now how about f inverse of f of c? Well, now we have f inverse of beta, and now you define f inverse of beta as b. So now we get b. Well, b doesn't equal c. Okay, so still it doesn't work. All right, so now we see that f also has to be injective. Okay, so now our pink arguments, so if this is crazy to you right now, that's understandable. You can re-watch this part of the video, or you can try to see some of the examples that I give. Maybe it'll make more sense. Okay, so from the pink, f needs to be injective. And in fact, kind of all we needed to look at up here was this. So f inverse must send every element, so it must send every element. So then our f has to hit every element, so that has to be surjective. But f inverse has to send it to a unique element in its codomain. Okay, well, for that to be unique, then f can only hit each element in the codomain one time. It can't send two elements in the domain to one element in the codomain. Okay? So boom, roasted. Therefore, so what does it mean for f to be surjective and injective? F needs to be bijective for f inverse to exist. And so what I mean by f inverse to exist is I mean f inverse to exist as a function, okay? We don't really care about f inverse, at least in this class, unless it's a function, okay? I can't always speak in general terms when you go into future math classes, but for this one, I can. Okay, so we could even take this a step further, and we could actually even show that f is bijective if and only if it has an inverse function. So think about it. So maybe you don't really know how to show that f is bijective in our direct way of just showing that it's surjective and then it's injective. Well, if you can show that f has an f inverse that is a function, you have shown that it's injective and surjective, or else f inverse wouldn't be a function. Okay, so how cool is that? So f bijective if and only if f inverse exists. If and only if f inverse exists. And exists as a function, okay? I know I'm beating a dead horse now, but okay. How cool is that? So now we have a totally different proof. Now we have a new way to prove f is bijective. Cool. Okay, so first you would want to find that f inverse goes from y to x for your original function f from, like, let's say x to y. Then you want to show two things. Okay, so you would say consider, or you would like claim that this was going to work out, and then you would want to actually prove that f of f inverse of y is y, for all y in our y. And then f inverse of f of x equals x for all x in our x. And something that just occurred to me is, I mean, you should know this notation, but what you might not know, I'm not sure what they teach you in calculus, is this. So this is like f inverse composed with f. So you go from right to left with that. So these are the same thing. Okay, sometimes we put parentheses around here. Okay. All right, cool. So you would need to first find some function that this works. Okay, find. So yeah, it needs to be a function. So first find a function f inverse that goes from the right domain to the right codomain, and then you need to show that when you compose them that way, it's true for everyone. Okay, fabulous. So let's go over an example. Okay, so for this example, we don't have to show that it is bijective, because it's already given to us that it's bijective. So we don't have to like prove that we can find an inverse function. We just need to find one and then show that it does work. So show that it satisfies 1 and 2 from above. Okay? All right. So this is another case where scratch work could really help. I suggest you could try these on your own. But spoiler alert, I'm about to tell you what it is. So f inverse of x equals 1 over x. You could change the variable if you'd like. It is what it is. It's not really a problem if you call it x or s or y or z, just as long as you're not saying like a specific number or something, because then that would be weird. Okay. All right, so now I need to check my two things. So first, if I do f inverse of f of some positive real number. Oh, also, some things you want to always be on the look for is like problems with zero, problems with dividing by zero, stuff like that, or also negatives, so like negatives and square roots or something, and maybe you're not in the complex numbers, you don't have imaginaries. Yeah, you just want to always be careful about things. The reason why it might look like I'm not being careful about things is because I have already solved these problems. But yeah, you can always do some scratch work and stuff and take some time to think about it. But I'm just going to kind of fly a little bit through this. So what does that end up being? Well, that's f inverse of 1 over x. But who is that? That's 1 over x, who in fact is x. Boom, roasted. Okay. So sometimes if you have a function and maybe it does something different to even numbers and odd numbers, which is an example I'll show in the next video, you'll have to split these up a little bit more. But we're just talking about numbers that are bigger than 0, so I'm all set. I don't need to split it up. You might want to take some time to think about that, but yeah. Okay, so f of f inverse. Well, what's great about this problem is they're the same. Boom, roasted. So f is equivalent to, sorry. So if you do the 3 lines, that means like equivalent to. So that means they have the same domain, the same codomain, and the same identification rules. Crazy. Okay? But you just proved that this is, in fact, its inverse function because you showed these 2 things. Okay, so well, it's not the factorial of f inverse, but but yeah, so it's a good time. Now we're done. All right, so I found that. So maybe I would box it in. Yeah, that feels right. I don't know. I always need to add something to the end, some sort of box, I guess. All right, so let's look at this second example. I'm going to kind of change it up a little bit. So I'm going to let A be the set A, B, da da da. So it's, woo, okay. My laundry's done. So that's the alphabet, right? And then let's call B maybe is the set 1, 2, all the way up to 26. Okay. G goes from A to B. And it's defined as G of A equals 1. G of B equals 2. Da da da. G of Z equals, you guessed it, 26. Okay? So here's how I'm going to write it. So I'm going to get kind of lazy. So G of some equals number in alphabet. Alphabet. Yeah. Okay. So I'm going to find, so I have the same assignment as before. I'm assuming that this thing is bijective and I just need to find the inverse function. Okay? Although it would not be too hard to show that this is bijective. But, okay. So G inverse of, and I'm just going to shorten this to number, equals letter on that number of the alphabet. So you know what I'm saying. I just try to come up with a goofy example to show you that it doesn't always have to be like this rigid, like, construct. Okay, so G inverse of G of, what does G take? Well, G takes letters in A of that letter. But then G inverse just gives us that letter, okay? And then we have a number. We would get G of letter at that number in the alphabet. And then that would just give us that number. Boom, roasted. So we prove that that is the inverse, in fact. So you would want to write a conclusion. Okay, there will be more examples in the next video, but now I'm going to give you a non-example. So it's going to be kind of weird. The whole time you can always just be believing that this thing does not have an inverse. And we're just going to slowly try to figure out how we can get it to have an inverse. Okay, that's kind of my goal with this. And it's to kind of give you another perspective on why it doesn't always work. Like for a generic function. So let's have some function h from the reals to the reals such that h of x equals x squared. So let's see, does h inverse of, let's say, y equal square root of y, does that work? Question mark. So it still would be h inverse goes from reals to reals. H inverse of h of negative 1 equals h inverse of 1, which equals 1. Oh, well, that's not equal to negative 1. Okay. Well, shoot. Okay, that didn't work. All right, well, maybe it was just an injectivity problem. So let's try h goes, let's change its domain. All right, so we change its domain. Does that work now? H inverse goes from the reals to the positive reals. So H inverse of 0, okay, that's well defined. We get H of 0, wait, that's an error. H of 0 isn't defined to go anywhere. Okay, well, what if we just union on 0? Okay, well, maybe that would work. But then H of H inverse of, how about -1? Okay, that's just an error, right? That's not well defined. Or if you do know that -1 goes to I, square root of -1 goes to I, well, that's not in our codomain. Remember, functions have to always hit inside their codomain. Okay. So H inverse. So how about H from real plus to real plus H of x equals x squared. Then exercise on your own, you can show that H inverse goes from R plus to R plus, such that H inverse of x equals square root of x. So that does work. Okay, so we really do need it to be injective and surjective. So the second problem that we had here, that was a problem of H was not surjective. Okay? And our codomain and our domain matter a lot. All right? Okay, great. So try it on your own. Try doing the proof of why that does work. I'll see you next time.